In this demonstration, we are going to cover high-resolution imaging. First thing to keep in mind whenever you're attempting any high-resolution imaging is you always want to plasma clean your specimens if your specimens can withstand the plasma. The reason for that being, when you're doing high-resolution imaging, you're putting a lot of current into a small area, and you have the potential to build up contamination very quickly if you don't have a clean specimen. So always plasma clean your specimens if you're going to do high resolution imaging, if your specimens can stand it. The other thing to keep in mind too is the specimen we're going to be looking at today is a single crystal semiconductor wafer with thin films on it. Whenever you're working with a single crystal specimen, you always need to use a double tilt holder for that, because what we're going to see when we get into the rest of the demo is that you need good zone axis alignment to get the best high resolution image. So that's not to say you can't do high resolution imaging with a single tilt holder, and in fact, if you're working with things like nanoparticles or specimens where zone axis alignment is really not practical, then it really doesn't matter one way or the other. But if you're working with a single crystal specimen and you're attempting high resolution imaging, you should use a double tilt holder. So loading of the double tilt holder into the column is in essence no different from that of the single tilt holder. Okay, so that's the end of the holder right here. You can see there's a little pin. Okay, just like on the single tilt, that's going to line up with this line here on the airlock. Okay, and just like the single tilt, I'm going to line that up. I'm going to push that in. Okay, right up to the edge of the tape line that I have there. You can hear the airlock open. Now if I come in here to microscope control, I have to tell the system now that I've got a double tilt holder. So I've got double tilt, and now what I have to do also is, you see on the double tilt holder here, I've got this cable coming off of the back, okay, which is used for the control of the beta tilt. I have to plug that in, and that's going to plug in right here on this 9-pin connection. And so that's pretty easy to do. Just line it up here. And make sure it's in there. Okay, it looks good. And then you come back here and you tell it the holder is connected. Okay, and we can see red light on the airlock is out, so we can finish with the rest of the loading. Counterclockwise turn, and then the holder goes in. Okay, so holders in the column now, so we can go ahead and open up the isolation valves. Okay, so first thing we need to do is find the specimen. And so again, we talked about doing this. So I'm in SA mode right now, as you can see. So I'm going to go into LM mode, and we'll go pretty low. We're down at around 150x. Okay, and again, if I can't see a beam here, I'm going to use my intensity knob on the left-hand panel here. There we go. Okay, so what you can see here, the grid that's in here is an Omni probe grid. Okay, so I'm going to move the stage here so you can see this. So those protrusions that are pointing to the left, those are what are called the posts of the grid. If I move over here, you can see under each post, see that's the letter D. Okay, and then there's a C, and there's a B, and there's an A. So this is actually a 4-post grid. The specimen that I want is actually mounted on the A post. Okay, and it's actually right there in the middle of that little notch in the end of the post. So I'm going to go ahead, go back into SA mode here. Okay, and now it should be pretty close to where I was, but I'm going to drag the stage a little bit to the right here, and there we go. So there's the sample right there. So obviously first thing you have to do is find the sample. And then from here, of course, just like we were doing a regular TEM session, we need to set eccentric height. So again, come over to your right hand panel, eccentric focus, okay, and then adjust your Z-axis buttons here until you've minimized the contrast. Alright, so that looks like we're close. Right about there, and then I go a little more and it goes back into contrast. So right about there. Alignment of the instrument in high resolution mode is essentially no different from any other type of imaging. You do want to use a low numerical value spot size, and then the same basic procedure as before. You need to apply the gun alignment. We already set eccentric height, but again, center the C2 aperture, correct the condenser lens astigmatism. Obviously after that, we have to balance the deflector coils, perform rotation centering, and put in an objective aperture. But an added thing that we have to consider now, because we're working with a single crystal specimen, is zone axis alignment. So you can actually see here, I'll increase the magnification a little here. Okay, so you can actually see the different layers of the specimen. So that layer, or that region, if I move, okay, so that dark line that's bisecting the circle there, that's actually a film. That left side of that line is the single crystal substrate, and so we want to align the sample so we're along the zone axis, and that's going to give us the best high resolution image. So to do that, you need diffraction mode. And so before you start, you usually want to do this illuminating an area that's going to be similar to what you're going to do when you do high res. Right now my indicated mag is 125 kx, which is kind of the lower limit for doing high resolution imaging on this particular instrument. On other instruments it may be different. And so I'm also illuminating an area about the size of that 40 millimeter circle. So now to check my zone axis alignment, we go into diffraction mode. Okay, you can see I'm in diffraction mode now. Okay, and now we can see, okay, we can see the diffraction pattern. So keep in mind now, I'm getting a contribution to that diffraction pattern from everywhere that is being illuminated. Okay, so I'm getting a contribution from the substrate, I'm getting a contribution from the films. What I'm primarily concerned with though is the substrate. And so you can actually see what look like a set of spots that form part of a circle. Okay, so the circle's kind of curving to the right. So kind of, if you look at my finger, it's kind of curving like this. Okay, and that's actually what's called a Lowy circle. Okay, and so the zone axis then is actually this way. So I have to tilt the sample to effectively close the Lowy circle. Okay, so here's where, if you remember from the tutorial on two-beam imaging, your alpha and your beta tilt controls come in. Okay, So you always want to start with the alpha control. Okay, I'm going to start with the plus alpha here. Okay, so you can see now by adjusting that. Now I've got the Lowy circle, basically my fingers here, it's curving like this. Okay, so now what I'm going to do is I'm going to go to the beta control, and I'm not sure which way to tilt with the beta. I'm going to start with the plus, see if it gets any better. Okay, and you can see now what happened is I don't have the spots anymore. So what I have to do now is I have to go back into image mode. Okay, and you can see now I'm no longer okay, so I have to move the sample back, and this is part of doing this, unfortunately, is there's a lot of switching between diffraction and imaging to reposition the specimen. So I'm going to go back into diffraction now. Okay, and so again, I'm going to adjust my beta plus, and I think it's getting worse. I'm going to go minus with the beta. Alright, and I think that's getting better. Is it getting better? Oh, I'm not sure. No, there we go. The plus is getting better. Alright, and again, I'm off the sample. One thing you can also do, it's a little tricky, you can try to move the sample while you're in diffraction mode. It's not always reliable. Maybe you can see there now I've moved and I'm closer. And so I'm closer now to closing the Lowy circle. I'm using the plus beta because I know that's getting me the right way. Okay, I'm a little bit closer. All right, and so I'm still a little bit closer. Okay, and then one last check here. I'll go back into imaging mode. All right, and so I'm basically over my region. Now what you're going to notice though, particularly when you do a lot of tilting, again, is now I have to reestablish eccentric height. Okay, so I already pushed my eccentric focus button before. I haven't touched the focus. So I can just use the Z axis knobs here. Oops, that's the wrong way. There we go. Okay, so now I have to move back. Okay, there's my area of interest again. I'm going to go back into diffraction. Alright, and so you can see right there, I've got pretty good zone axis alignment. And again, the better, more precise you are with this, the better the high resolution image you're going to get. And so now that we've got good zone axis alignment in this area, the next things we need to do are the pivot point balancing and the rotation center, and then the insertion of an objective aperture. So I'm going to go out of diffraction mode and back into image mode, and we'll take it from there. Okay, so we're back in image mode. So just like in the basic tutorial for, or the tutorial for, so we're back in image mode, and so just like was covered in the tutorial for basic operation, we can focus the image. So I've got my focus knob here, I've got my focus step set at 3, and I just want a slight under focus here. It already looks like I've got a slight under focus, but I can just go ahead and see that's too under focused. If you're not sure, you can leave it at the value for eccentric focus, and you should be pretty close anyway, but that looks pretty good. Okay, so next thing I'm going to do, okay, come up to the tune tab here, beam tilt PPX. Okay, and again I see a little separation of the beam, so I'm using my multifunction knobs here to minimize the separation. I don't care about where the beam is on the screen or what's happening with the image. I only care about the separation of the beam. So that looks good right there. I'm going to come back here, select done, do the same thing for the Y. Okay, and that looks good right there. And then go ahead and hit done. Okay, I'll recenter my beam here. And then the next thing is the rotation center. So probably the most critical alignment step, aside from the crystallographic alignment of the specimen, is the rotation center when you are performing high-res imaging. So again, we're going to come here into the Tune tab, select rotation center. Okay, and so right now actually the rotation center looks pretty good. Okay, so what I'm going to do though here, okay, I can spread the beam a little more. Okay, I'm seeing now some shifting of the image that I don't want. Okay, so again, you're concerned with the shifting of the image here, not the sample. This is a little tricky of a sample to do this on because I have these linear features. If I had something that was a little bit more three-dimensional, that would be helpful, but sometimes you have to make do with what you have. Alright, so let me adjust the X here. That's worse. Alright, that looks pretty good right there. Okay, there is another way to do the rotation center, which we will talk about later in the demo, which is called the Coma-free axis alignment. But for now, we'll just do the standard method of performing the rotation center. You can also do this, it's probably preferable to do this with the binoculars and the focusing screen, because you will be able to see with a little more precision, but obviously that's hard to demonstrate with the camera here. So I've got the rotation center done, and you come back over here, select done. Okay, and so now we're going to insert an objective aperture. So when performing high resolution imaging, it's very critical that you use a correctly sized objective aperture. And as we discussed previously, your objective aperture centering and selection is always done in diffraction mode. So again, I'm going to go into diffraction mode. Okay, there's my diffraction pattern. I've got that good zone axis alignment. And so now I come up to my objective aperture here. So this has 4 apertures. The 4 position is the first aperture. That's usually way too small to do high res. When you're doing high res, you're centering the objective aperture. You can actually hear, I'm going to increase my camera length here. Okay, so you can see I've got the direct beam, and then I've got opposing pairs of spots. Your objective aperture has to be big enough that when it's centered around the direct beam, you're including at least 1 pair of Bragg beams. In principle, the bigger the aperture, the more beam pairs you're going to get in, the more detail you're going to get in. That, of course, has to be counterbalanced with the fact that if you make your objective aperture too big, that also worsens your point-to-point resolution. That's why typically there's an aperture that's sized correctly as a compromise between those, so you can balance out the effect of spherical aberration with the effect of having diffraction, limited resolution. But for high-res purposes, it has to be at least as big to include a pair of Bragg beams. And that's obviously zone axis dependent, it's material dependent. On this particular sample, this is a silicon sample along a 110 zone axis. So what I'm going to do here is I'm going to put in Aperture 2. Aperture 2 usually works well. I think that's a little bit bigger than the so-called optimally sized aperture or Scherzer aperture. So I'm going to go ahead here. Okay, Aperture 2's in. All right, and we can see it's not centered. So I've got to use my adjustment knobs here to center it. And I have it centered around the direct beam, okay? Centered around the direct beam. So you can see I've got a few different pairs of Bragg beams included in the aperture. What I would also do normally, I'm going to drop my camera length a little bit here. Okay, I would normally do this for the most accurate result. Again, use the binoculars and use the focusing screen, and then you'll get the most precise alignment of the aperture. So I'm going to go ahead and do that, and then I'm going to return back to image mode, and we'll start imaging with the digital camera. Okay, so objective aperture has been centered, and here's our image now. So we're ready to pull it up on the digital camera. So once again here, go to the camera tab, hit search. Okay, and we're waiting for the camera to insert. We're listening for that sound. Okay, there's the sound. The camera's in. Come back here to my right-hand panel. Select R1, lifts up the viewing screen, and there's my image. Okay. I'm going to go ahead here. I'm going to increase my exposure time. Again, if I click on view and on my keyboard here, every time I hit the up arrow, that doubles my exposure time. So I'm going to go ahead and hit up arrow here to get 0.08. I can see that I'm actually a little too under focused, so I'm going to use my focus knob here. Here we go. Okay, to get about where I want right here. Okay, so we can see several layers in the specimen. I'm going to go ahead and move this over here. So this is the silicon right here, and then these are layers that have been deposited via sputtering. Okay. So one other thing we can do now, and we haven't talked about this yet, but if I come up here, I select view, I come up to process, I click live and then FFT. So this is a live fast Fourier transform of my image. Okay, and I can actually use this now to do something really useful, which is correct my objective lens astigmatism. Okay, so now to do this, you need a region that is mostly amorphous, okay, or very finely grained. So now all the way over here on the right, you can see that region on the right, okay, to the right of this line. That is actually platinum deposited in the fib. It has a high carbon content, and so it does contain, it does have an amorphous component. And so that is reflected in the FFT here, and I can see now if I have any objective astigmatism to correct. Okay, so looking at the image, it looks astigmatic, and it is. Okay, and so actually, you can see here, I'm adjusting the focus now. Okay, so I can actually see here, I can see that the rings in my FFT are not round. Okay, and actually there, if I go right there, I'm actually starting to form like an X. Okay, you can see that now. And that means I have some objective astigmatism. Okay, and so the way to correct this is come back to the Tune tab, go down to Stigmator, select objective. Usually you want the step size here down at 1. And now it's a matter of using your multifunction X and Y to make the rings in the FFT circular. So I'm just going to start with the X here, and that seems to be making it worse. Alright, so that's not too bad right there. So really, I'm going to tweak the Y here a little bit. That's making it worse. Yeah, so right about there looks pretty good. And actually now I can see in the image, I don't really see any astigmatism. So now I can do a little more precise focusing. I'm going to put my focus step down to 2. And I'm probably a little too under focused. And right about there. Ideally, when you do your focusing or your astigmatism correction, you want to do that close to your focal condition. Okay, so I'm going to move back over here. And I'm going to go ahead and do an acquire. Okay, I've got 1 second here. Okay, and there's my high resolution image. So now this is, again, magnification wise, this is really the lower limit where you can start to see lattice fringe detail. Okay, so there actually is, like, I can digitally zoom in on this and you can actually see the lattice detail in the image. Okay, so it is there, but again, this is the lower limit where you can see this. Okay, so what I'm going to do here instead is I'm going to go up in mag. Okay, so I'm going to come back over here, flip my viewing screen back down. Okay, and I'm going to go up. I'm still in SA mode. And we'll leave it at 250 in SA mode. And now again, I need to recenter, resize my beam. And again, I'm always working clockwise from crossover when I do this. And I'll go ahead and lift up the screen again. Okay, and now it's much easier for me to see that lattice level detail. What you'll also probably notice too is that your astigmatism needs to be corrected again, particularly if you go up in mag. So you can see in the FFT there, I don't really have a round rings. So I still have my multifunction X and Y. And make the rings round, and that looks pretty good right there. Okay, and so there's my silicon. I'm going to drop my focus step now down to 1. Okay, that's my finest focus step. There we go. Now, one of the ways I can also use this FFT is to help me focus, believe it or not. Okay, so I know I'm under focused right now. And I can actually see that first ring in the FFT. So I'm actually going to go clockwise with my focus knob to expand that ring basically as big as I can get it while still being under focused. Right about there. And so now I've got a nice focus. And there I can start to see the lattice detail a little more evidently. But what I'm going to do now again is I'm going to go up in magnification one more time. Okay, so I'm going to go ahead, put the screen down. I'm going to go up to 400 kx. This is the highest I can go in SA mode. Resize the beam once again. Lift the screen back up. Okay. So this region in the middle is predominantly amorphous. You can see in my FFT, my astigmatism correction still looks pretty good. One thing you also notice is every time I talk, I don't know if you can see that, the image shakes. Okay, so it's very sensitive to vibration and sound. So obviously you don't want to be doing this when you're acquiring your actual image or you get a blurry image. Okay, so I'm going to shut up here and I'll do an acquire. Okay, and so you can see now this is a polycrystalline film. This is partially amorphous, and this is crystalline, and this is also crystalline. I'm not seeing any of the substrate here. I'm going to go ahead and close this. All right, there's my substrate now, the silicon substrate. And so now you can see in the FFT, I can see these spots in the FFT, which are the spatial frequencies predominantly from the silicon. All right, and so there we go. Now one thing to keep in mind here when you're doing this is that wherever you align the zone axis, that zone axis alignment probably isn't going to be good everywhere on the sample. So the samples aren't flat, they're usually bent, and doesn't have to be bent a whole lot to really produce a big change. So I've moved, a few tens of nanometers away. In fact, the alignment's probably a little bit better here. Yeah, so that actually looks a little bit better. But the takeaway here is, if you're moving, a substantial difference from where you did the initial zone axis alignment, you're probably going to find that crystallographically it's not the same anymore. So keep that in mind. If you do a move like that, you need to go back and you need to reestablish the zone axis alignment. But what we can do now, so we're in SA mode, and SA mode works fine for doing high-res imaging, but if I want to go higher in magnification than this, okay, I can go the next mode up, which is called MH mode, and that's what we're going to discuss next. When we do that, there's some additional alignments that need to be done. So I'm going to go ahead, I'm going to flip the viewing screen down here, and then we'll talk about operating in MH mode. Okay, so in SA mode, the highest I can go is 400 kx indicated. If I go higher than that, I enter in MH mode, and this will go up close to a million K or a million X indicated. So I'm going to go up here, and we'll go to 610. Okay, when you go from SA into MH mode, there are some alignments that you should redo. And so what I'm going to do now is I've got my objective aperture inserted, so I'm going to take that out. Okay, I'm going to put this back here to the out position. Okay, so the first thing you're going to notice is that in MH mode, your focus is going to be a little different. Okay, so I'm going to use my focus knob here, get a focused image right about there. Okay, and now the alignments that we need to redo here, okay, I'm moving basically off the sample here. Okay, the alignments we want to do now are Coma-free alignments. You could do standard alignments that are not Coma-free when you're in MH mode, but to get the best resolution at this point, you'd want to do Coma-free alignment. So there's a pivot point alignment, okay, just like what we did before, but it's for Coma-free. So if I click that, Okay, and so again, use multifunction X and Y, minimize separation of the beam. All right, looks pretty good. Come back here, done. Do the same thing for Y. Again, I only care about the separation of the beam, not the image. That looks pretty good right there. Okay, come back and click done. All right, again, expand my beam so it's a little bit bigger than that 40 millimeter circle. And so now here is where, again, you need a portion of the specimen that is amorphous. So again, I've got the fib platinum in here, which works great for that. I'm gonna go ahead and lift up the viewing screen again. Okay, and so I can see I've got my FFT going of my live image here. All right, so you can see here now in the FFT, right, I clearly don't have circular rings. So the first thing I have to do is correct that. Okay, so again, that's with the objective stigmators. Come back over here, tune tab, objective. Okay, use my multifunction knobs. Oops. Activate it here. All right, there we go. Keep in mind, I don't have an objective aperture in right now. I'm not going to put that in until the end. Okay, so right there I've got circular rings. Okay, now what I'm going to do here is I'm going to first make sure my beam's still centered, and it is. I'm going to come back here. So now what I'm going to do is the Coma-free alignment. Okay, so I come back to the tune tab, and there's an X and a Y. I'm going to start with the X. Okay, so what is this now? What's happening is the beam is being tilted back and forth along the X direction between two tilt extremes. It's about 10 milliradians. And so you can see the image is clearly changing between the tilt extremes, and the FFT is also changing. So now the goal of doing the Coma-free alignment is to get the FFT at each extreme to look basically the same. Okay, so in this case I only have the X multifunction activated, so I'm going to go ahead here and bottom it out, and we'll just see what happens here when I adjust this. Okay, so you can see I don't really see them looking the same here. That looks reasonably close. You may not get it perfect. I'll show you what it looks like though when it's like really far off. It clearly doesn't look the same. It's probably too far. Keep going, that's still too far. Yep. So again, you get it as close as you can get it. That looks pretty good right there. Come back over here. Done. Okay, I'm going to put the screen back down. I'm going to recenter the beam. When you're at really high mag, you want to be cognizant of beam drift because it will be more evident at high magnification. Go ahead and lift the screen back up. Now I'm going to do the Coma-free Y. And so those look pretty close. Okay, now they don't look as close. That looks pretty close right there. And now not so much. And that looks pretty good right there. Again, it doesn't have to be perfect, just as close as you can get it so that they're the same or similar. Go ahead and hit done. And once again, I'm gonna check my beam centering here. It looks okay. All right, and now that I have the Coma-free axis alignment done, now I can go back into diffraction mode, put my objective aperture back in, which I'm gonna do. I'm not gonna show that because I already did it. And then we can return back into image mode. And so I will pull the image back up on the camera after I've done that, and we'll go from there. Okay, so got the image back on the camera, and now the lattice fringes are really evident. You have a really small field of view. One thing I need to do again, I'm going to move back over to my fib platinum, or just an area that has some amorphous, like this area here in the middle. And you can see on my FFT, oops, put my focus step at 1. My rings are a little elongated, so again, come back to the stigmator, in the tune tab, objective, and that looks pretty good right there. And you can clearly see you have a very thin film here that's polycrystalline. This is partly polycrystalline, this one's polycrystalline, this is also polycrystalline. These are obviously high Z materials, but you can still see the lattice fringes in them. I'm going to move back to the silicon substrate here. Yeah, there we go. Okay, now one thing you can see here, as I change the focus, I'm going to shut up here. Okay, that might be a little hard to see, but the appearance of the lattice fringes changes with the focus. Okay, that's one of the tricky aspects of doing high res, is that you are seeing phase contrast, and it is dependent in part on your objective lens focus. The way to get around that, to get a more intuitive image, of course, is to do a type of STEM imaging, which we will cover in another demo. Go ahead and do an acquire. And there we go. So we have a nice lattice image of the silicon. There's some kind of oxidation layer here between this and this layer. I believe it's platinum. So one thing you can clearly see, if I go back here, to this thin film, and even in all of these films, you can see, because these are polycrystalline, you can see how the lattice fringe appearance changes with position, because I have different crystallographic orientation. Okay, so you can see here lattice fringes look different than here. I'm also seeing moire fringes because I'm having overlap of some grains. Okay, so you can see some of them here. Let me try and do the contrast a little bit better. Yeah, so you can see them now really more evidently there and there. I adjusted the gamma feature here on the contrast. Okay. And with that, that concludes the demonstration of performing high resolution imaging on the FEI Tecnai F20.